Hi guys. Last week we did not have too much content, especially on the weekends because I was a little bit busy. But this week I believe will be easier to make some content for you guys. So to give you a general perspective, what we'll be doing this week, we'll take on some global competitions, that is Div1 plus Div2 competitions, so like VK Cup, Deltix runs, LA token, even Harbor Space had some global competition. So that's because I usually don't participate in Div1 plus Div2 contest because they're a little bit harsh on the Div1 ratings, unfortunately. Yeah, so I wanted kind of to get a little bit better at them. That's why we'll have a full week dedicated to them. I hope you'll find it interesting. So let's jump straight into the first couple of problems that are more or less easy. If you disregard my run submissions here, they have two 1600 rated problems. So that should be doable for most specialists and experts, maybe even some pupils. Within a reasonable amount of time. I'm not saying that you need to like solve such problems instantly, but I bet you will be able to solve them if you spend like 1 hour. So I just wanted to share some thought process, like how do I approach such problems. Maybe that will help you. So in this problem from a Spring Deltix round, problem C, compression and expansion, we had lists, to-do lists, which were nested and numbered, so like you can see examples of correct lists and incorrect lists. So each item in such a list is of the form like several numbers concatenated with a dot. So like 1, then 1.1, 1.1.1, etc. You get the drill. Now, unfortunately for us, we don't have the entire list. What we have is only the last digit. So if you take a look here, the last digits are 1, 1, 2, 3, and that's exactly the last digits here. And if you take a look here, you get like a bunch of ones, bunch of twos, 1, 2, 1, 2. That's exactly what happens here. Like we are given the last digit of each item and we want to restore the list, the entire list. Because of that, like first thing I noticed about this problem is that the number of the input size was limited by 1000. So I immediately realized why is that, because obviously the size of the output list, we have like n items, each of them can potentially be quite long, so like n numbers long. So it means that the output size is limited from above by n squared, and unfortunately, we can't print too much output because that's quite slow. So that's why n is picked in such a way that n squared is at most 1 million. I believe we can actually print like 10 million characters, but that is on the edge. So yeah, that kind of explains the constraint. And because of that, like you immediately realize, well, I can't do anything quadratic. That's very nice of the problem setters. So let's see what I can actually do. Now, when you look at the structure of the output list, and you start thinking about it, you think like, okay, how do I transform these last digits into the full list? Now, very nice of them. They also explain, they provide a definition of this list, which kind of explains how do you want to construct it. Because they say like you can start a deeper nested list if you append one, or you can increase the current item. You start thinking, okay, so that sounds a lot like DFS. If you can visualize every such nested list as a rooted tree with empty roots apparently. Then we have item 1. Let's not put a dot here. Then we have item 2. And item 1 has items 1 and 2. Item 1 has again items 1 and 2. This item 2 has only item 1. That is this particular tree. Hold on for a second. I need to fix some background noises. Apologies for that. If you are hearing strange noises in the background, that should be fixed now. So getting back to our problem, like every nested list can be represented by such a tree. So naturally what we do is we construct it by going here, then we get back, go here, get back, go here, get back, here, 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 here. So a natural DFS order, right? The problem being, of course, that we do not know the structure of the tree. So it appears that we can't run a DFS. However, if you understand what DFS is doing deeply enough, you may remember one trick that is sometimes used to save some time on like huge DFS, and that is DFS with explicit stack. If you keep the stack yourself, it may be faster than going down the recursion stack. So what we can do is like whenever we see 1, we know that it starts in new list, right? In new deeper nested list. And whenever we see any other number, that is actually, it is technically like, it's not only the son of its parent, but it's also a right sibling of its left brother. Like what actually happens here is that you can represent this tree like that, and I believe that there is a special name to this structure which I never remember. So let's like successor pointer or something, but let's not get deep into that. You don't need that to understand the problem. So this actually makes it quite easy to understand what's happening, like how you actually traverse your tree. And if you had a number 3 somewhere, that will be also connected like that and not to its parent. So what happens is whenever you see 1, you start a new list because you can't append it to the previous list. You can't keep the previous list going, right? And whenever you see anything but 1, you actually want to increase some of the previous lists. The problem here is like technically, the answer may not be unique, because when you see this 2 for the first time, you have no idea of the existence of this part, so you may think, why don't I append it here? Why don't I keep this list going instead of that one? Well, the answer being is like, sometimes you may get successful with such an approach, but sometimes it's impossible. Like here, each one has to be used, so you can't just keep going, right? However, like in this specific case, my solution actually outputs a little bit different than this tree. It actually says, well, this can be appended here to keep it going. And it does it because that's the deepest one. Like, it is never bad to use the deepest one because it means that you can use this one afterwards. Because if we were to use this body here right now, and then let's say a 2 comes in, one more 2, we can't append it here because that is not in order. Like we have to keep going in this part of the tree, which we unfortunately can't keep going because it has no ones, and neither the root path has. And therefore, like our logic will be that we always, if we see number 1, we always start in new. We always start a new, deeper nested list. Whenever we see any other number, we always use the deepest one that we can use. Or rather, not the deepest one, but the deepest number that we can use, as this 3 shows. Like we don't append 3 to 1, we append 3 to 2 reasonably. So how to actually implement it? Well, we'll keep the track of the DFS stack. So originally the stack is empty, then we append this body in, and we append this body in, and we keep on going. And whenever we see a 2 or any greater number, we try to change the upmost element of the stack, which does not look like upmost, but you got the idea, to this value. If we can't change that specific element, for example, we got here, right? So now our stack looks like this. We changed this element. Now we see the next entry in the input is 2. So we naturally can't do anything with this 2. So we just get rid of it. It will never get visited by DFS again. So we roll back. We see that, well, this is 1, and you can change 1 to 2. So we do that. So now our stack looks like this. Then it will look like this. And we'll see another 2. Actually, my solution will append it here. And it will keep going. But if there was no 1 here, and we just had another 2, then we would roll back once again. See, well, then we'll see that, well, that's 1, we can change that to 2. So we go this way, then we append 1, we change 1 to 2, we change 2 to 3. So we keep the track of DFS stack explicitly, and that's basically it. So that problem kind of checks how well you understand the concept, which is quite nice. There are also other ways of doing that without DFS stack. That's what I was trying originally. But that was a bad solution. We are not going to look at it, because the good solution looks like this. We do literally what we arrived at in the previous couple of minutes. So we have our stack, which is represented as a vector, because technically we have to print it. And the easiest way to do it is by using that kind of syntax, which does not work for std stack, fortunately, but expectedly. So whenever we see 1, we start a new dapper nested list, which corresponds to pushing 1 onto the stack. Otherwise, we keep removing items, keep going up the DFS tree until we hit the item, which we can change to the current AI. If we do that, well, we just change that with this kind of syntax. I think this can be actually a little bit simplified to get rid of one of these 4 lines, namely this one. Can be here, but I'll let that not very nice trick, but still a trick worth knowing. Have to get rid of this line and put it here. That should be quite easy for you to figure out. And then we just print this entirety of our stack separate with dots. So the usual way to do it, not to print the trailing dot, is that, well, you print first entry and then you print your separator with each other entry, skipping the very first element. So yeah, A nice problem on understanding the DFS concept, the trees, something about trees. I mean, you are given two operations in the statement that you can use, and naturally you know which one to use. So it was a nice short problem, but still, like if you're just starting out, maybe you don't know what the DFS is, maybe you don't know that you can implement DFS with a stack, stuff like that. So that may be useful for somebody. But we will keep going to the next problem, which comes from a VK cup elimination, which is Secret Santa. So according to the legend, we are given like a couple of people, several people, that want to give presents to other people. Nobody wants to give presents to themselves. That's kind of, you don't need a Secret Santa for that. But originally, like some people may want to give presents to the same person. So like these two guys want to give something to that one guy, or these two guys want to gift something to this body. And there may be people such that, well, nobody has them as their first priority, unfortunately. But like Secret Santa does not work like that. Secret Santa expects that we want to find a permutation, and specifically a permutation without fixed points. So like everyone gives one present, everyone gets one present. So one way to fix this permutation would be to fix this into a permutation, would be to change that edge. I guess I should do that in red. To, let's say, that edge, and excuse me, and also to change that edge to that edge. In this way we are getting a very legit permutation, like 2 cycles, right? And the problem asks us to change the minimum number of edges. So like we want to keep the maximum number of edges possible. And print one such assignment. So the first thing I thought about when solving this problem is like there are some local contradictions with what we want to achieve. Namely, there are people such that they have in degree, that is number of people who want to give presents to them, greater than 1. That can't happen, so one of these edges will be removed. So here and here we have one edge that will be removed. And I thought like, okay, let me remove an arbitrary edge. Let's not say that we necessarily remove such guys. Say that I removed this edge. Yes, I should bring the vertex itself back. And let's say I remove this edge. So like I know that for a given that I need to remove one of such edges. And I start thinking like, do I care which one I remove? And it turns out that I don't. Because like, now I am left with something that I want to fix, right? And I say that, well, if I have enough vertices, like I have 1, 2, 3 vertices, more specifically, I have 2 vertices which have out degree 0, so that they don't give presents to anyone at the moment, and 2 vertices that have in degree 0, so that nobody gives present to them. So if I have at least 2 such vertices, it's always possible to find derangement. It is a permutation without fixed points. So here that is extremely easy, right? This way we can connect them in. And that happens whenever you have at least two vertices. More specifically, whenever you have either at least two vertices, or the one lacking the in degree and the one lacking the out degree are different vertices. So like here it's also obviously possible to complete them. However, if it was something like this, then there is no way I can't draw this loop, so I have to put it into the cycle somehow. And here I started thinking, well, like I actually deleted one edge. It was going here. So maybe that was not very wise of me. Maybe I should have deleted the other edge and redirected it here. Right, this way I removed one good edge, but I brought one good edge back, so that is fair play. We still get the same number of good edges, the edges from the original graph. Now there are two ways to implement this problem. Specifically, when you have something like that, you need to find this permutation somehow, because the other one does not work, right? They can't have that, you need to have that. So there are two ways you can find this, either by noticing that, well, we ended up with a graph such that each out degree is at most 1, but also each in degree is at most 1. Such graphs are actually a combination of simple paths and cycles. You may perform some explicit analysis on that one, but I did not really feel like doing it, so I did a different thing. You may have noticed that I said the word derangement, and that is because like this is more or less similar to derangements. In derangements, however, the set of vertices that needs in degree and out degree is the same set. Here they are actually different sets, but that doesn't really matter too much. Because the number of like such derangements is, I believe, at least the number of original derangements, and the number of original derangements is on n elements is approximately n factorial over e, where e is the Euler's constant, meaning that if you select one permutation on random, it has 1 over e probability, or roughly, let's say, I never actually remember this. I think it's 36%, something like that. So if you pick a permutation at random, you have a 36% chance of getting the one without fixed points. Meaning that on average you need e, or like approximately, people will be mad at me, but e is approximately 3 tries, random tries to get a good permutation, and also like the probability of getting a good permutation in at most let's say 9 tries is quite close to like quite close to 1. So like, on average you need a constant number of tries. So I thought like, well, that's a nice trick. So let's go ahead and implement it. So what I did here is like I need an inverse permutation, or not permutation, just inverse graph, so that I know like which edges come into which vertex. And here you may notice that I actually overwrite, so I pick the latest edge that is going into some vertex. You can pick any edge. And I say like, well, I actually said like this because that's the same quantity. I said that, well, if we don't, like each vertex that has in degree 0 corresponds to one edge that has to be changed. That is dual argument to saying that every second and further edge going into the same vertex has to be changed. So that's another way to notice it. Like if you have a vertex with in degree 0, you have to redirect one edge to go into this vertex. So I compute this inverse permutation. I use it to partially restore the permutation B that I want. And I say like who lacks in degree and who lacks out degree. That's actually like out degree 0 in degree 0. And I check, well, if like there's only one vertex and one isolated vertex, you can check it with such condition, and I want to insert it into the cycle. So I check where it goes. I say like, okay, we'll use that edge. And I also say like, well, whoever was going into this vertex, they should be going into our vertex. Otherwise, we need to generate a permutation without fixed points. We know it exists and takes expected iterations. So I just do random shuffle of in degrees of vertices with in degree 0, and like I check whether it has a fixed point in linear time. So overall, overall the solution is still linear, but it's expected linear time. If I don't have fixed points, well, I can add the edges that I generated in my permutation. That's a nice trick. You could do it by working explicitly with cycles and paths, but I really did not want to do that, and that is a nice knowledge. If you want a derangement, you can generate it on average quite quickly by just doing random stuff. Now, obviously, if you want a derangement in a usual sense, you can just pick like 1 goes to 2, 2 goes to 3, etc., and then n goes to 1. But here, the set of vertices that have in degree and out degree 0, they differ, so it's not clear how to construct it explicitly. So I decided, well, let's just have something random. It's a nice trick. It's the first time I've ever used it in a contest, so it was quite pleasant that I noticed it. Actually, the editorial by Tourist also mentions this trick, because he obviously knows about it as well, about the number of derangements. That's nice. But if you don't want to do that, you can generate such a derangement explicitly by working with paths and cycles, but I don't really want to do that. It can be quite annoying in permutation problems to work with some objects explicitly. Sometimes it may be easier to generate something on random if you know that there are a lot of such objects and you're getting one quickly. When it's like, sometimes it's just easier to check than to think about like how do I generate one. I think it was a nice trick. If you really want, you can try to implement the path and cycle solution, but I bet it will be actually longer, but I don't know for sure. So that is roughly what I wanted to share with you today, just to give you a quick idea of what we'll have later this week. I posted a community post about it. yeah, you can see that tomorrow we'll have some more problems from Deltix rounds and VK Cup, but this was like from Deltix Sprint and VK qualifying. So this time we'll have Deltix Summer and VK final. On Wednesday we'll have two interactive problems because I just noticed that I have some easy interactive problems unsolved, so I wanted to solve them. On Thursday, we'll have some difficulty, some harder problems from two problems from VK Cup. I believe one is actually from qualifying and the other one is from the final rounds. On Friday, we'll have even harder problems, and then on Saturday, I suppose we'll have this problem. I'm not exactly sure about this part of the schedule. This one, I briefly looked through it and it looks right. Here I just picked several problems from the corresponding competitions of the given difficulty. I hope they are good, but I will need to look into them to let you know for sure. So maybe something here will change, but in general the intended schedule is like that. Let me quickly fix this. Like, that's very annoying to format them, community posts, because it's just unpredictable. Like it is not what you see is what you get. It's something harder. Like white space can be quite tricky sometimes. But yeah, that's approximately what I wanted to share with you today. I hope you learned something new, and I hope you will tune back tomorrow for more content. So, just like that, see you guys tomorrow. Bye bye.